Myself, Dr. K. Prasad, Department of Physics. Today, I am going to deal on research methodology and nanomaterials. In this topic, research methodology and nanomaterials, today I am going to discuss on nanomaterials. So, in nanomaterials, nanoscale, what is meant by a nanoscale, what are the applications of nanotechnology, we are going to discuss in detail. First, what is meant by a nano scale? So, the word nano is derived from Greek word with a meaning of extremely small. Means how much it is a small? It is a billionth part of a unit. Means 10 to the power of minus 9. A or nanometer is 1000 millionth of a meter. So that one we can see here 1 nanometer is equal to 10 to the power of minus 9 meter. That is nothing but billionth meter. 10 to the power of minus 6. This is the millionth meter, and in angstrom 10 angstroms. 1 nanometer span time is spans of how many atoms? 3 to 5 atoms lined up in a row is nothing but 1 nanometer. Means 5 atoms in 1 nanometer can able to fit. So that much small it is. For comparison, so we know the whatever we are seeing in around the atmosphere, around the things, just we will compare for few things. Just we know for one single human hair is about how many nanometers? It is around 80,000 nanometers. 1 nanometer is 10 to the power of minus 9 meters, but human hair is how much? Means 80,000 nanometers. So it is 80,000 times it is wider comparatively 1 nanometers. So that much small is nanometer. And if you are comparing with red blood cells is approximately 7,000 nanometers. Means it is 7,000 means cell is very blood cell is very small actually. Even we are comparing with 1 nanometers with the red blood cells, which is 7,000 nanometers. Means it is 7,000 times larger. Scientists and engineers are nowadays are interested in nanoscale because it takes 100 nanometers to zero point 0.2 nanometers approximately is the nanoscale. Below this, whatever the atomic scale is less than that 0.1 nanometers, therefore the nano world is a broad borderland between quantum world and macro world. Now we are going to discuss on nanotechnology. What is meant by nanotechnology? Nanotechnology is the day-to-day developing subject with large number of application. In each and every application, this nanotechnology is applicable. How much it is potential means nanotechnology has the potential to create new materials and different type of devices, different type of wide range of application, and these applications also includes such as medicine, electronic, energy production. In each and everything around us is mostly involved with knowingly or unknowingly with nanoscience and nanotechnology. Nanotechnology, what is meant by that? Nanotechnology is the design and development of techniques, different techniques and instruments and devices used for fabrication, characterization and application of nanoparticles is nothing but nanotechnology. Next, in nanoscience, what are the things it is we are going to diagnose? means many diagnostic instruments, means nanoscience, how we can able to see this much nano. So kind of one kind of instrument is required to see the how much nanometers is smaller, how we can see. So this one we need to detect point of view we are having for different types of instruments are developed by many scientists. One few kind of instruments are, one is transmission electron microscopy. In short form, we can call it as a TEM. Scanning tunneling microscopy. In short form, we can call it as a STM. And STM and also atomic force microscopy almost similar, but few in atomic range we are going there. It is a scanning tunneling effect is there. So, scanning tunneling microscope and atomic micro force microscope, and also we are having for magnetic resonance imaging technique have been invented in the nanotechnology. These are the major diagnostic instrument, and also we can able to see in scanning electron microscopy. That is we are calling as a SEM. SEM also we can able to see for some extent of nanometer range of nanoparticles and a different type of structures we can able to see in SEM also. Nanoscience. Next, we are coming to the some briefly about nanoscience where it is applicable. Nanoscience is the basic nanotechnology. The nanoscience morely relies on what theory? Quantum theory. So, nanoscience can be defined as the study of phenomena and manipulation of materials. At what range we are going to do for this phenomena we are applying and manipulation we are doing, means it is under the range of atomic, molecular and macromolecular scales, where the properties differ significantly from those at large scale, is nothing but nanoscale. Origin of nanotechnology. So first of all, this nanotechnology, from where it is started. So we will see for how it is origin, it is came for nanotechnology. The word of nanotechnology is relatively new. The existence of nanostructures is not new, but at the 4th century, means 4th century, at Roman glassmakers fabricated glasses containing nano-sized materials. Similarly, gold nanoparticles are made long ago. The concept of nanotechnology was first given by Richard Feynman. Means nanotechnology who is invented first? Richard Feynman. He was given the terminology that is nanotechnology. In the 18th century, means 18th century, British scientists, who are the scientist name? Thomas Wedgwood and Sir Humphrey Davy, were able to provide images using nitrates and chlorates, but their images were not permanent. It is erased by once you are taking image, then afterwards you are able to see, but later on it is able to erase. So that kind of technology was first, it is invented by Thomas Wedgwood and Sir Humphrey Davy, where they are used the images like nitrates, chlorates. Next, in 1960 afterwards, what is the development is came in 18th century afterwards in 1960. It is Richard Feynman presented visionary and prophetic lecture at a meeting of American Physical Society entitled the There is a Plenty of Room at the Bottom is the title, where he speculated on the possibility and potential of nano-sized materials. The term nanotechnology was defined by Tokyo Science University professor Norigo Taniguchi in 1974 paper as follows. What is that paper? Nanotechnology mainly consisting of the processing of separation, consolidation, and deformation of a materials by one atom or one molecule is nothing but nanotechnology. Now, nanomaterials. Now we are coming to the picture for nanomaterials. What is meant by nanomaterial? Nanomaterials means a material whose size is in nano range. This is the answer which may generally thought, but there is a there is an implicate meaning. So what is meant by nanomaterial? Suppose consider a gold biscuit of 100 centimeter cube cut into pieces. No properties are changed except its size. Divided it into further smaller pieces, then also there would be not be any changes in its property. Thus, microscopic solid pieces of the material possesses size independent properties. It was found that when gold is divided into fine grains of nearly 50 nanometers, the properties like density, color, hardness, melting point, resistivity, etc. are changing. So the microscopic pieces possess size dependent properties. So these the made in nanomaterials. Thus the size dependency where it is an essential property for nanomaterials. So nanomaterials is defined as material having one of its dimensions in a nano range, that is, and it is possible size dependent property, or nanomaterial can be defined as those materials which have structured component with size less than 100 nanometers. At least one dimension it should occur. If one dimension is in a nano range, it is called quantum well, that is, we are calling as a thin films. If two dimension are in a nano range, it is called quantum wire, means one dimensional, it is a quantum well, that is, we are calling as a thin film. If two dimensional or in a nano range, it is called quantum wire, that is carbon nanotubes. If three dimensional or nano range, it is called quantum dot, that is nothing but colloids. Next, where the application we are using for this nanotechnology? The applications of nanotechnology we are using in the field of medicine, like drug delivery system, active agents, contrast medium, medical rapid test kits, and prostheses and implants system, and antimicrobial agents, and coating of different kinds of materials, and cancer therapy to used as a active agent. And in the sector of chemical industry, majorly people are using for impresentation of paper, switchable adhesive nature, and magnetic fluids, and fillers for paint system and coating systems based on nanocomposites. In engineering category, mostly it is useful for mechanical, material science engineering, and all kind of system where wear protection for tools and machine, scratch resistant, it is a scratch resistant coatings, and plastic parts, anti-blocking coatings, etc., are lubricant free bearings sector. These are the major applications in nanotechnology, and also it is in useful in electronic industry, such as data memory, like you are using in a computer sector, RAM, ROM, these all are very, very useful to use the device. So computers also they are using, and the displays, LEDs, FEDs, and OLEDs, and laser diodes, glass fibers, optical switches, filters, IR blocking, conductive anti-static coatings. Many applications are applicable in electronic industry. and it is also used in civil engineering department as a construction of materials and thermal insulation, flame retardants, surface functionalized building materials for wood and floors, stone, facades, tiles, roof tiles, etc. Because anti-stick properties, many properties, facade coatings, groove mortar, and many other applications are useful in construction department. And automotive industry means automobile industry application. What is the major application for automotive application means automobile industry? It is first, it should have lightweight construction and painting for different fillers, base coating, clear coat, catalyst, and tires, fillers, sensors, coatings for windscreen and car bodies, also useful in automobile industry. And textile, fabric, non-wovens, where it can be useful as a smart cloths and surface processed textile fabrics, are many other applications also applicable. In applications like energy, it is used in solar cell, lithium ion battery, lead acid battery, many other kinds of batteries, and fuel cells, capacitors, and cosmetic applications like sun protection, lipsticks, skin creams, toothpaste, many other applications like cosmetic industry, and food and drinks industry also, clarification of fruit juices, additive package materials, storage life sensors, and also in applications of nanotechnology like household items like ceramic coatings for iron, orders, catalyst, cleaner for glass and ceramics, floors, floors and windows, like these are the household items. Like another application, sports and outdoor playing items like skybags, anti-fogging of glasses, googles, anti-fouling coatings for ship and boats, and ring-forced tennis rackets and balls industry also applicable for this application. And first, before going for this, surface area to volume ratio and what is meant by quantum confinement, we are going to discuss in first, surface area to volume ratio. So, why the properties of nanoparticles are very different from this? Because the phenomena due to which properties of nanoparticles are different. One is due to surface area to volume ratio first. Second one is quantum confinement effect. So, what is the use because of these two phenomena? So why nanoparticle properties are changing, and why the structural, electrical, magnetic, optical, all the properties are going to change? Why? Because surface area to volume ratio, one major application for nanomaterials, have relatively large surface area. First, it is a area is large when compared to the same value of mass of the material produced in larger form. And consider a sphere of radius. Just we are taking a sphere of radius r, r. We are taking as a sphere of radius r, and its surface area is 4 pi r square, 4 pi r square, and its volume is 4 third pi r cube. And if it is surface area by volume ratio is 4 pi r square by 4 pi r cube. That is nothing but 3 by r. Surface area to volume ratio is the, what is the formula? 3 by r. For a cube side ratio, 6a square by a cube. That is nothing but 6 by a is the cube side. Now, what we are going to do? As radius or A decreases, surface area to volume ratio increases. So the properties of material will be changing. The material has high surface energy if it is a small size or vice versa. As the surface area to volume ratio increases, the material possess good catalytic properties, one major benefit, and also due to the nanoparticle show enhanced stability of the material and a broader scope of application. In some cases, materials that are inert in their larger form are reactive. When produced in the nanoscale form, this affects their strength or electrical properties drastically. It will changes. For example, the particle size is 30 nanometers, has 5 percentage of its atomic surface. At 10 nanometers, 20 percentage of its atoms, and 3 nanometers, 50 percentage of its atom is the example for surface area to volume ratio. What is quantum confinement? First, we should understand what is meant by a quantum confinement. When atoms are isolated, the energy levels are a discrete energy level. The discrete energy levels, so you can see the discrete energy levels of a particle trapped in a one-dimensional infinite potential well is an example. So, these the one-dimensional and these the infinite potential well where the energy levels are there like M1, M2, M3, M4 are represented. One side is energy, another side we are representing with mass. This is the quantum confinement. And when very large number of atoms are closely packed to form a solid, the energy levels are split and form a bands. So here we can able to see the bands, and these are the two interacting atoms where the two atoms are interacting closely packed, and three interacting atoms, their energy levels are also shown here. Likewise, n number of interacting atoms are available. The energy levels and their separation energy levels are split in the form of bands. So, quantum confinement is further conformed with nanomaterials represent intermediate stage when the dimension of a box or potential wells in which a particle is trapped are confined are of the order of de Broglie wavelength of electrons. Energy levels of electrons changes. This effect is called quantum confinement effect. So, dimension of a box or potential wells in which a particle is trapped or confined in the order of de Broglie wavelength of electrons, the energy levels of electrons are drastically changes. These effects changes are called as a quantum confinement effect. When the material is sufficiently small in size, typically 10 nanometers or less than that 10 nanometers, organization of energy levels into which electrons will jump from one level to another level and climb or fall change. Specifically, the phenomena results from electrons and holes squeezed into dimension that approaches a critical measurement called excited Bohr radius. These majorly excited Bohr radius is due to the quantum confinement. And it is further we can discuss in small nanocrystals or clusters in grains, or the electronic energy levels are not continuous as in the bulk materials, but in nanomaterials are discrete energy levels are confined because of the confinement of the electronic wave function to physical properties also drastically changes. Due to that, physical dimension of the particles also will changes. This can affect the structural, optical, electrical, magnetic behavior of materials, particularly as the structure or particle size approaches the smaller end of the nanoscale. The major examples for this quantum confinement examples are opaque substance opaque means it is a transparent opaque substance became a transparent like copper material. Inert materials became catalyst. What is the catalytic material? Best catalytic material, that is platinum. Stable material but combustible, which is a aluminum. Solid turns into liquid at room temperature, that is called gold. And insulators become conductor, that is silicon. Due to this quantum confinement. Now we are going to the fabrication of different kinds of nanomaterials and nanoparticles based on two particular approaches. One is top-down approach, another one is bottom-up approach. So what is meant by top-down approach? Fabrication of different kinds of materials. Basically, it is fabricated in two ways. One is top-down approach, another one is bottom-up approach. So first, we will go for bottom-up approach. Second one first. So bottom-up approach. Here we can see bottom-up approach. Atoms are cluster. Atoms are there. Group of atoms is becoming a cluster. Clusters are making into a smaller nanoparticles. So in this approach, atoms or molecules or nanoparticles are used in building blocks. Means one nanoparticle is looking like one building block for building. So likewise, just here we are taking as a one nanoparticle as a one building block as the creation of complex nanostructure. These properties are highly controlled. Complex chemical synthesis techniques are useful. In this approach, materials and devices are built from molecular range of components which assemble themselves chemically by principles of molecular recognition. These kinds of material arrange smaller components into more complex assemblies like more complex structures. Nanoscale structures are normally achieved by a chemical synthesis of materials in a liquid form or in a gaseous state. Next, top-down approach. What is meant by a top-down approach? In this approach, one rely on either a division or removal of a bulk material to produce. Means bottom approach is what we are going to see. Here we are taking the precursor chemicals which is in a smaller atoms like range, either nitrates, acetate, sulfates, chlorides, or oxides. These all are we are taking in a atoms form and it is becoming a cluster. Cluster is becoming a nanoparticle. Means you are preparing the compound by its own. What compound? Suppose lithium cobalt oxide, lithium nitrate we are taking, cobalt acetate we are taking, or cobalt nitrate we are taking to synthesize the lithium cobalt oxide. To synthesize the lithium cobalt oxide. In case we want to take for lithium manganese oxide, what is the precursor chemicals? Lithium nitrate and manganese acetate. So based on that, certain calculation based on that, this precursor chemical based on that you can prepare for the compound. So here we are taking the synthesis materials. Based on that, we are constructing what compound we want. That particular compound we are synthesizing in the bottom up approach. But in case of top down approach, what is the major change it is occurring? Top-down approach is already having the compound, and you are going for a different synthesis, different techniques to make the material in, means already compound is there. That compound is in what range? Is bulk. Bulk is nothing but it is a, like, just you take it as a copper metal is there, some larger, you are making into a powder form, and that powder you are making into a nanoparticles. So there are different kinds of techniques are available to go from top down approach. So what are that also we are going to see in a later slides. In this approach, majorly it is a division or removal of bulk material to produce a nanostructure or nanoparticles. These are this top-down approach is a much simpler process compared to bottom approach. Means bottom approach is more complicated because there we need to synthesize the compound, while in case of top top-down approach, we are already having the compound. We are going for nanoparticles range. So here already the compound is in the bulk form. We need to make it grind into a powder form, and this powder is further we need to classify in a nanoparticle range. These nanoparticles are forming in a blocks. This blocks is making in a full building of the material like. In this approach, nano objects are constructed from larger entities without atomic level control. This seeks create a smaller devices by using larger ones to direct their assembly to make the top-down process of preparing nanoparticles are effectively examples of solid-state processing of materials. So, in this top-down approach, what are the techniques are available? So, top-down approach, different fabrication methods are available to make nanoparticles, means bulk materials. We need to convert in what form? In nanoparticle form. To synthesize in top-down approach, what are the major techniques? One is ball milling method. Another one is physical vapor deposition technique. Third one is chemical vapor deposition technique. So what is meant by ball milling method? Means just you take it as a, you are taking one rock, that rock point of view, how many balls is required? Means what is the quantity of that rock, that rock point of view you want to make it. It looks like is milling the method. Means you are using in grinding mixie, or you are using in, generally we will go for pindi girni. This girnis, these all are making for larger particle into smaller particle. That smaller particle like tiny powder form they are going to make. So this ball milling also like one girni, but instead of their girni they will use for just a cutting machine type smaller to make. But here instead of that we are using for different types of balls. What is the size we need? The preferred method, based on that we can make it, crush the material into a smaller powder, that powder into a nanoparticle range. So in ball milling method, also called as a mechanical crushing method, and small stainless steel balls are made to rotate inside the drum and drop under the influence of gravity onto a solid present in the drum. The solid is broken into nanocrystallites. The ball milling method can be used in a wide range of elementals, means different types of elements we can cut it into a smaller to make the nanoparticles, and also any kind of metal oxide we can cut it into a powder form. For example, iron with the grain sizes 10 to 30 nanometers can be formed by using the ball milling method. A, a variety of intermetallic compounds based on based in nickel and aluminum can be formed by using the ball milling method is the preferred method for preparing for what kind of material, all kind of metal oxide preparation. Ball milling is the more efficient technique. Next technique, what are the advantages for ball milling method? What are the advantages for ball milling method? One is the major advantages for ball milling method. It can produce very fine powder and use it for both wet, means we can make the ball milling method either in a wet form, means either it is a dry form or in a wet wet form. Both the ways we can grind the material, bulk material, we can cut it into a powder form. And even it can be useful for even toxic substances also. We can ground into a better nanoparticles, as a cylinder is a closed system, so no environment effect, because it is a ball milling method is a closed system. Disadvantage, because these are whatever the larger particles we are grinding into a smaller particles. Due to that grinding point of view, we will get for more noise and high energy consumption. And also due to the balls will also will contaminate the whatever the precursor, whatever the material we have taken. So there is a chance of little bit contamination, but with the precautions we can avoid contamination also. Another deposition techniques is vapor deposition, refers to any process in which material in vapor state or condensed state through condensation, either it is a chemical reaction, conversion to form a solid material. This process are used to form any coatings, any thin films, alter the mechanical, electrical, thermal, optical, corrosion resistant and wearing properties of different kinds of substrate. What are the vapor phase deposition techniques available? One is physical vapor deposition technique, means already compound is prepared. That compound you are coating in a different, means you are creating the plasma and you are coating the material which is a thin film form. Chemical vapor deposition technique, you are using the different kinds of precursor chemicals and you are preparing the compound to form the concerned either a thin film form or in a powder form. So these are another kind of technique. So first we are going to discuss about what is meant by physical vapor deposition technique. Physical vapor deposition technique majorly involves the conversion of what kind? Solid material, means already it is in a compound. So that compound directly we are keeping in inside the chamber. We are creating the vacuum, and but after creating the vacuum, all the atmospheric materials all are removed, and it is in a vacuum. Pressure is maintaining. At the time we are passing either a argon gas or nitrogen gas. Due to that we are creating the plasma. So due to the plasma, whatever the atomic particles, means due to the plasma, either it is organ ion will go and collide the compound, and that collide particle, due to the we are created the vacuum, the particles can travel directly from target to substrate. So this target is what we are keeping. This target is a compound of your precised compound. Means suppose you are taking for lithium cobalt oxide, you are keeping the target as a lithium cobalt oxide. You want to coat this lithium cobalt oxide target material into the substrate, either it is a glass, silicon, ITO or any aluminum foil, copper foil, any kind of. So this material is going to deposit over the sheet. These are the different deposition technique, physical process, which is then cooled and redeposited on a substance as per our requirement. All the reactive physical vapor deposition techniques are hard processes combined has the following steps. What are the major steps involved in physical vapor deposition technique? Physical vapor deposition method for depositing the metal, we generally people will use for sputtering technique. That is, DC sputtering technique is very useful for all kinds of metal deposition. And if you are going for combination with the active gases such as nitrogen, oxygen, and methane, you are passing in the vacuum chamber, then plasma bombardment of the substrate to ensure the dense hard coating. And also physical vapor deposition method differs in means of producing the metal vapor and the details of plasma creation. It makes big task to understand. The primary physical vapor deposition methods are iron plating, ion implantation, and sputtering technique, and a laser surface alloying are the different physical vapor deposition techniques. So here, this is the chamber where we are keeping the target material, which is a copper we can coat over the substrate. Due to the plasma, and we are using the vacuum pumps, we are creating the vacuum inside the chamber. There is a absence of atmospheric pressure within the chamber. This is the chamber. This is the chamber, vacuum chamber, where we can remove the all the atmospheric pressure, whatever the contamination is there, these all things we can remove. Due to that, whatever the particle here it is there, if it is collided, if it is a plasma is created, argon ion is going and colliding this, if the target is copper atom, it is collided, then afterwards this atom can travel straightly to the substrate material. Due to this phenomena to occur, we are creating the vacuum. And this concerned material point of view, target point of view, we are supplying the sufficient voltage. Either it is a pulse laser deposition technique, some particular voltage we are using. Either it is a sputtering technique, we are using some particular voltage. Means that is a voltage and current. Due to that, that particular material is able to penetrate, means that the atom can able to travel from target material to substrate. Each and every material having the some particular voltage, like a copper, if it is a 50 electron 50 volts, and if it is a according to the material to material, it will change. Metal oxide, one kind of potential range will be there. So what kind of voltage and current, that power is required, that sufficient power we are supplying for each and every, either it is a metals or it is a metal oxide. Based on that, it will change the potential. So due to that, this power supply, what is the power supply is required, means how much power is required to remove the atoms from the target, to travel the atoms to the substrate. So that sufficient voltage and current we are supplying, then required power is required to remove the atoms from the target. So due to that, we can able to create the different kinds of thin film materials. Next, another technique is the thermal evaporation technique. Thermal evaporation technique, here either it is in a liquid form, either it is in a solid form. So we can take either it is in a liquid form like a precursor, or which is in a solid form, powder form we can take, and we can evaporate, and it will form in a gaseous form where it is deposited over the substrate. So these are the different type of depositions. So changes in morphology also it is possible by changing the different potential. So thermal evaporation is one of the simplest and most popular synthesis method, and it has been very successful and versatile in fabricating nanowells and nanowires. Thermal evaporation technique. So, what kind of nanostructure you require? Based on that, that precise synthesis technique we need to opt. So, here physical vapor deposition and thermal evaporation technique is useful for different kind of nanostructure. What kind of nanostructure? That is majorly nanobells and nanowires preparation point of view. Thermal evaporation technique is very useful, and we can also multi-wall and single carbon nanotubes have been successfully fabricated by using the thermal evaporation technique. Using what? How they are fabricated for single wall carbon nanotubes and multi wall carbon nanotubes by passing the hydrogen gas and methane or ethylene reactants. Due to that, it can able to form. And metal catalytic such as gold, tin, copper, etc. All the metals have also been used to achieve the size control alignment. And another technique is chemical vapor deposition technique. Chemical vapor deposition technique is the most useful technique to depositing in a thin film forms for a large variety of materials. Applications of chemical vapor deposition technique range from the fabrication of microelectronic devices to the deposition for protective coating materials. In typical chemical vapor deposition process, reactant gases at room temperature enter the reaction chamber. The gas mixture is heated, and as it approaches to the deposition surface, heated radiatively, means due to that it is creating the radiation, are placed upon a heated substrate, means we are keeping the substrate and we are keeping for the here precursors we are depositing over the substrate directly. Depending upon the process and operating condition, the reactant gases also we are going to decide what kind of condition we want, what kind of gases we need to pass, either it is argon, nitrogen, or methane, what kind of gases we want to, hydrogen, what kind of, depending upon the process and operating condition, the reactant gases may undergo homogeneous chemical reaction in vapor phase or before striking the surface. So, in this method, the material is heated to gaseous phase and allowed to condense on a solid surface in a vacuum. The nanomaterials are majorly useful for metal oxide, metal carbides, can be formed by heating the metal and carbon or metal and oxygen in a vacuum chamber to a gaseous phase to we are making in a solid phase, that is allowed to deposit on the surface of a solid. So pure metal powders like nanoparticles are formed by this method. This metal is melted, excited with microwave frequency, and vaporized to produce a plasma at 500 degrees centigrade. By cooling this plasma with water in a reaction column, nanoparticles are produced. So the grain size of the nanoparticles majorly depending upon the what kind of concentration of metal vapor we are taking, and its rate of flow in the reaction column, and what kind of temperature we are maintaining inside the chamber. This method can also be used for grow surface for different kind of metals, metal oxide, metal metal carbides, metal oxides. These are the great variety of chemical vapor deposition techniques, such as you can create the atmospheric pressure, chemical vapor deposition technique is available, and plasma we can create and we can deposit the technique. And another one is low pressure chemical vapor deposition technique. Another one is the technique is available, that is photochemical vapor deposition technique. Another one is by using the laser also we can deposit the technique, that is laser chemical vapor deposition technique. And chemical beam means the chemicals in the form of beam we are coating as a epitaxial growth of thin film. And another one technique is chemical vapor infiltration technique is also available. These different kind of techniques point of view. Usually these the schematic diagram for all chemical vapor deposition technique point of view. So here what kind of gases we want to pass, that is gas inlet, either it is oxygen, hydrogen, nitrogen or methane we can use. And these the sample where we are keeping the substrate. This is the sample which is a sample holder. This is the sample holder, and this is the sample where the sample will be a different type of surfaces we will use. Either it is a silicon, glass, indium titanium oxide gas substrate. Likewise, and here bottom quartz both will be used to heat the sample, and outside also both side it is heating, and gas outlet also we are keeping, and it is where the sample is placed inside the quartz tube. These are the various deposition technique available, and these the general schematic diagram for chemical vapor deposition technique.
Like, share, and subscribe. Hit the bell icon for more updates.